What is an LLM? How ChatGPT actually works. Hello, and welcome to Gate and Kernel. ChatGPT can answer questions, write code, summarize documents, translate languages, analyze images, and help complete complex tasks. But what is happening behind the screen? ChatGPT is powered by a type of artificial intelligence called a large language model, or LLM. An LLM does not think exactly like a human. It does not search through a giant database of prepared answers. Instead, it processes your input, recognizes patterns, and generates a response one small piece at a time. In this video, we will explain how that process works. Chapter 1. What does LLM mean? LLM stands for Large Language Model. The name has three parts. First, large. Large means the model contains a very large number of adjustable values called parameters. Training those parameters requires enormous amounts of data, computing power, and storage. Second, language. Language means the model is designed to process and generate human language. That includes everyday conversation, technical writing, programming code, mathematical expressions, document formats, and translation between languages. Third, model. A model is a mathematical system that has learned patterns from training data. An LLM can perform many language-related tasks because it has learned relationships between words, phrases, facts, programming syntax, writing styles, and ideas. Chapter 2. An LLM is a neural network. At its core, an LLM is a very large artificial neural network. A neural network contains many layers of mathematical operations. Each layer transforms the information it receives and passes the result to the next layer. The network does not contain normal software rules such as, if the user asks this question, return this answer. Instead, it learns statistical relationships during training. For example, it may learn that the word CPU, instructions, registers, cache, and memory often appear in related technical discussions. The model does not simply memorize those words. It learns possible relationships between them. These relationships allow the model to generate useful responses to questions it has never seen in exactly the same form. Chapter 3. Text becomes tokens. Before an LLM can process text, the text must be divided into smaller units called tokens. A token may be a complete word, part of a word, a number, a punctuation mark, or a short sequence of characters. For example, consider the sentence, "The GPU renders an image." It might be divided into tokens representing the GPU, renders, and image, and the final period. Each of those pieces may become a token. One English word may correspond to one token, or it may be divided into several tokens. In other languages, a character, word, or punctuation mark may also become a separate token. A token is therefore not exactly the same thing as a word. Tokens are the basic units that an LLM reads and generates. Chapter 4. Tokens become numbers. A computer cannot directly understand the meaning of a word. Each token is therefore converted into a collection of numbers called a vector, or embedding. These numbers represent relationships learned by the model during training. For example, the word CPU and processor have related meanings. Their numerical representations may therefore be relatively close. The words CPU and banana have very different meanings. Their representations may be much farther apart in vector space. The model also needs information about token order. Consider these two sentences: the dog chased the cat. The cat chased the dog. They contain almost the same words, but their meanings are different because the order has changed. The model must therefore represent both the tokens and their positions in the sequence. Chapter 5. The Transformer Architecture. Most modern LLMs are built using a neural network architecture called the transformer. The transformer was introduced in the 2017 research paper, "Attention is All You Need." Unlike earlier architectures that processed sequences mainly one step at a time, the transformer relies heavily on attention mechanisms and supports much greater parallelism. Transformers are made from many repeated processing blocks. Each block usually contains two important components. The first is an attention mechanism. The second is a feed-forward neural network. Information passes through these blocks repeatedly, allowing the model to build increasingly useful representations of the text. Early layers may recognize basic words and local relationships. Later layers may identify grammar, subjects and objects, technical concepts, connections across the passage, and the overall meaning of the text. Chapter 6. What is attention? Attention helps the model determine which earlier tokens are important when processing the current token. Consider this sentence: the server could not start because it had lost power. To understand the word "it," the model must determine that it probably refers to the server. Attention allows the model to compare tokens and assign different levels of importance to them. It does not simply look at the nearest word. It can use relationships between tokens across a much longer passage. Modern transformers normally use multi-head attention. This means several attention operations examine the same text in parallel, potentially focusing on different relationships. One attention head may focus on grammar. Another may focus on relationships between subjects and pronouns. Another may track time, technical context, or connections between sentences. Together, these parallel operations help the model build a more complete understanding of the available context. Chapter 7. What are parameters? An LLM contains a very large collection of adjustable numerical values called parameters, or weights. Parameters control how information moves through the neural network. At the beginning of training, these values are not useful. The model produces poor or nearly random predictions. During training, the system repeatedly adjusts the parameters so that the model becomes better at predicting text. If a prediction is poor, the training algorithm calculates the error and changes the model's parameters slightly. After this process is repeated many times, the model gradually becomes better at predicting. Language. The knowledge of the model is therefore distributed across many numerical relationships. It is not normally stored as a simple collection of documents or a table containing one answer for every possible question. It does not store information like this: question 1 equals answer 1. Question 2 equals answer 2. Question 3 equals answer 3. Training primarily changes the model's parameters so that they can represent patterns found in the training material. Chapter 8. How an LLM is trained. The first major training stage is commonly called pretraining. The model receives a sequence of tokens and attempts to predict a missing token, or the next token. Suppose the training text contains, the operating system manages the computers. The next token might be hardware, memory, resources, devices, software, or something else that fits the context. The model produces probabilities for many possible tokens. For example, hardware, 40%. Resources, 30%. Memory, 20%. Software, 7%. Other possibilities, 3%. The training system knows the correct continuation from the original text. If the model gives the correct answer a low probability, the system calculates the error and adjusts the model's parameters slightly. Then it performs another prediction. This process is repeated across enormous numbers of examples. Over time, the model becomes better at grammar, sentence structure, writing styles, programming patterns, relationships between concepts, and predicting useful continuations. The objective sounds simple: predict the next token. However, becoming good at that task requires the model to learn a surprisingly large amount about language, knowledge, logic, and the patterns represented in its training data. Chapter 9. Learning to follow instructions. A pre-trained language model may be able to complete text, but that does not automatically make it a useful assistant. It must also learn to follow instructions. Without additional training, a model may continue a user's question instead of answering it. One common method is supervised fine-tuning. Human-written examples show the model how a helpful assistant should respond to different requests. Those examples may demonstrate what the user is asking, how a useful assistant should answer, which responses are clear, which responses are inaccurate, and which responses may create risks. Human evaluators may also compare several answers and indicate which response is better. OpenAI's Instruct GPT research described a process that combined demonstrations, human rankings, a reward model, and reinforcement learning from human feedback. This improved instruction following compared with relying on pre-training alone. Modern systems may also use other preference optimization, training, and evaluation techniques. The complete training process for current commercial models is not publicly disclosed, and different companies may use different methods. Chapter 10. What happens when you send a prompt? When you enter a message into ChatGPT, the system first prepares the information the model needs. At a simplified level, the process looks like this. Step 1. Your message enters the system. Step 2. The message is divided into tokens. Step 3. The tokens are converted into embeddings. Step 4. The embeddings pass through transformer layers. Step 5. The model calculates a probability distribution for many possible next tokens. Step 6. The model selects the next token. Step 7. The process repeats. The model does not necessarily process only the message you just entered. Depending on the available features and settings, the context may also include earlier messages in the conversation, instructions that guide the assistant, information from uploaded files, results returned by tools, relevant memory when enabled, images, code, and other inputs. The model combines this information into the available context and calculates probabilities for many possible next tokens. It selects one token, adds it to the response, and then performs the calculation again. For example, it may first generate CPU. Then, CPU is. Then, CPU is the computer's. It continues until it has formed a complete sentence, paragraph, or answer. Although the result appears to be a complete response, it is normally generated incrementally, one token at a time. Chapter 11. Why can an LLM hallucinate? An LLM generates a likely continuation based on patterns in context. It does not automatically verify every statement against an authoritative source. This can produce a hallucination. A hallucination is an answer that sounds confident and well written but contains incorrect or invented information. Hallucinations can happen for several reasons. The training data may be incomplete. The prompt may be ambiguous. The model may combine related patterns incorrectly. The required information may be too recent. The available context may not contain enough evidence. Or the model may generate plausible language without sufficient support. For example, the model may know that a person, a company, and a technology all exist, but incorrectly combine them into an event that never happened. This is why important claims should not be judged only by how fluent or confident they sound. They should be checked against original sources, official documentation, reliable news organizations, research papers, real data, and trustworthy databases. Giving the model access to web search, documents, databases, calculators, or specialized tools can improve accuracy. However, tools do not guarantee that every conclusion will be correct. Important information still needs to be verified. Chapter 12. ChatGPT is more than an LLM. An LLM is the language processing engine. ChatGPT is the complete product built around one or more artificial intelligence models. A useful analogy is, the LLM is the engine. ChatGPT is the complete vehicle. A vehicle needs more than an engine. It also needs steering, brakes, instruments, a body, and control systems. In the same way, ChatGPT is more than an isolated language model. Depending on the task and available features, it may combine a model with system instructions, safety mechanisms, conversation history, memory, web search, file analysis, image understanding, code execution, and external tools. The capabilities seen by the user are therefore produced by the model and the surrounding product system working together. The exact internal architecture, model selection process, and routing system used by current versions of ChatGPT are proprietary. No public explanation can describe every internal step. But the fundamental process remains understandable. First, convert input into tokens. Next, process the tokens with neural network layers. Then, use attention to interpret the context. Calculate probabilities for possible output tokens. Finally, generate the response one token at a time. This process requires enormous amounts of matrix computation. That is why GPUs and specialized artificial intelligence accelerators are so important. Their parallel arithmetic units and high bandwidth memory can perform the large matrix operations used during LLM training and inference. Conclusion: a large language model is not a conventional database, a traditional search engine, or a human brain. It is a mathematical model trained on enormous amounts of data. Through parameters, vectors, transformers, and attention mechanisms, an LLM learns complex patterns and relationships between words, concepts, facts, and ideas. It then uses the available context to generate a response one token at a time. Understanding the following fundamental concepts provides the foundation for learning more about artificial intelligence and large language models. Tokens, vectors and embeddings, parameters, transformers, attention mechanisms, pretraining, fine-tuning, inference, and hallucinations. Together, these concepts explain how an LLM processes language, learns patterns, and generates useful responses. In the next article and video, we will examine tokens more closely. We will explain how tokenization affects context length, model performance, generation speed, and cost. Thank you for watching Gate and Kernel. If you found this video helpful, please like the video and subscribe to the channel. See you in the next video.